Thank you. Hello everyone, I'm Javad Qarichamani, second year PhD student in HKUST. I'm working with my supervisor Dimitris Papadopoulos. Today I will talk about new constructions for forward and backward private symmetric searchable encryption. This is a joint work with Dimitris, Charlampous, and Rasul. First, let me explain what is dynamic searchable encryption. DSE consists of three protocols: setup, search, and update. Consider following scenario. There is a user and he has a database of text files. He encrypts them and creates an encrypted index. Then he outsources them to an untrusted server. This is called setup protocol. Later, he may want to search for a specific keyword. So he runs setup protocol and get back all files containing that keyword in encrypted format. Then he decrypts them locally. Finally, he may also want to update files. So for example, add keyword to a file or remove a keyword from a file. This is called update protocol. To achieve efficient DSE schemes, we allow the server to learn some additional information called leakage. For example, the information learned by server during setup is called setup leakage. For example, the size of database. Or during search, the server may learn access pattern and search pattern. Access pattern is which files are retrieved, and search pattern is whether a search query is repeated or not. There is another type of leakage which is associated with updates. This is the main focus of this paper and this work. I will explain about it in the next slides. The high-level idea of preventing leakage during updates is the server should not learn anything related to update with previous operations. Let me give you an example. Consider the sequence of operations for keyword W1. First, user adds keyword W1 to file F1, then searches for keyword W1, and finally he searches for keyword finally he adds keyword W1 to file F2. At this point, the server should learn nothing about the update update during time 3, which happened and should not be able to correlate it with previous operations, the two previous operations. More formally, the update leakage should be a function of operation and file identifier. There is a different type of leakage has to do with deletion. At a high level, search queries should not reveal any information about indexes of deleted files. This is captured by a notion of backward privacy, formally defined by Bose et al. In last year's CCS. I will explain it by another example. Consider this sequence of operations. User first add keyword W1 to file F1, add W1 to F2, delete W1 from F1, and finally search for keyword W1. The result of search is F2, and the server at this point should not learn anything about file F1 because it is already deleted. Regarding search operation, three leakage functions were defined. The first one is timedb, which reveals files currently containing keyword W and when they were stored. In your example, the timedb of keyword W1 is F2 and 2 because file F2 is stored at time 2. The next function is updates, which reveals timestamp of each update for keyword W. In our example, update of keyword W1 is 1, 2, and 3 because we added in time 1 and 2 and deleted at time 3. The last function is delhist, which reveals exactly which deletion cancels which addition. So in our case, delhist of W1 is 1 and 3 because the addition at time 1 is cancelled by the deletion at time 3. Based on the three leakage functions, Bose et al. Defined three backward privacy types. The first one is type 1, which reveals only timedb. The second one is backward privacy type 2, which reveals timedb and updates. And the last one, type 3, reveals all of these functions. As we see, as we go from top to bottom, we get less secure schemes. Let's see what has been done and what is our contribution. The same paper of last year's CCS proposed 4 backward private schemes. Moneta, which is BP1, Fides, which is BP2, Dianadel and Janus, which are BP3. We proposed 3 backward private schemes, ORION, MITRA, and Horus. ORION is BP1 and is improved version of Moneta, both in theory and in practice. Furthermore, it is the first scheme with quasi-optimal search time. It means that its search computation time depends only on the number of files currently containing keyword W. The next scheme is MITRA, which is BP2 and has the same asymptotic as Fides, but it is up to 253 times faster. Even it is faster than Janus and Dianadel, which are less secure and are BP3. Our last scheme is Horus, which is an optimized version of ORION. It is more efficient and it has less interaction, but it is leaking more information, so it is BP3. The detail of Horus is in our paper. In the remainder of the talk, I will explain about MITRA and ORION, and I will start by MITRA because it is simpler. Okay. MITRA is using a dictionary at the server to store key value pairs. Furthermore, it has an array at the client to store a counter for each keyword. There are 2 keys, K1 and K2, which are used by the client for encryptions. Now suppose that we want to add keyword W1 to file F1. First, the client increments the counter corresponding to keyword W1. Then he has to compute 2 values, a key and a value. The value is the result of encryption of keyword, file, identifier, and operation. So here the file is F1 and operation is add. Next, he has to determine at which location at the server this value should be stored. So he evaluates the key using a pref function, pref of keyword and the counter which is stored at the client. Then he sends these 2 pairs to server and server stores it on dictionary. The procedure is the same for adding W1 to file F2. He just increments the counter and evaluates these 2 values and sends to server and server stores it on the dictionary. For adding a new keyword, for example W2 to F1, he increments the counter corresponding for W2 and sends to server, and the same procedure happens. We are using blue color for keyword W2 and green color for keyword W1. Now suppose we want to execute deletion. We want to remove keyword W1 from file F1. We treat delete exactly like insertion. So we evaluate key and value and replace the operation by delete and compute value and key and send both of them to server and server storage. Now suppose we want to search for keyword W1. The client sees the counter which is 3 for W1, evaluate 3 different keys, key 1, key 2, and key 3, and send them to server. Server execute a lookup, 3 lookups, and return back the encrypted values. Client decrypts them and find the final result, which is F2. As we can see, it is very simple construction. It is obviously forward private because during update the server only sees a pair key value. Value is semantically secure and key is a result of pref with different inputs. It is backward private type 2 because during search the server only sees a number of pref evaluation, which he has already seen before. Before I explain ORION, let me mention to its motivation. Search computation time of currently existing schemes, including MITRA, which I explained, grows with the total number of updates for each keyword. Let me give you an example why it is a bad idea. Suppose we have the timeline of operations for keyword W. We add some files, we add this keyword to some files, And after that, we remove all of these files except one. Finally, we execute a search for keyword W. At this point, the computation time is proportional to the total number of updates, while the result size is 1. So is it possible to propose a scheme with computation time depends only on number of existing items? It is known to be possible for forward privacy, but what about backward privacy? The answer is yes. ORION and Horus are the first schemes to achieve that. The key idea of ORION is to do some extra works during updates to save time during searches. We do that by using a nice trick during deletions. Consider the previous dictionary, and suppose we added 3 files for W1, which is denoted by green, and 1 file for W2, which is by blue, denoted by blue. This dictionary can be conceptually assumed as a number of inverted lists, each of which denoting locations stored corresponding for that keyword. You can see the corresponding list here. Now I will focus on the list and explain the example by this list. Consider we want to add keyword W2 to file F3. At this point, the client increments the counter and sends this file to server. Server stores this file in the list of corresponding keyword, which is W2. The procedure is the same for adding keyword W2 to file F4. Now suppose we want to execute deletion, which is the main idea and main point of this scheme. First, server replaces the position of file F1, which is going to be deleted, by the last index, which is F4. So F4 will replace at the position of CNT1. Next, client decrements the counter to 2. What is particularly useful about this way of handling deletion is at the search time, the search computation time is proportional to the number of files currently containing keyword W2. Now consider we want to search for keyword W2. The client sees the counter, which is 2, and asks from server to give back the position, the first and second position of the corresponding list, which is W2. Although this idea works functionally, but it destroys forward privacy because the server is accessing the same location as previous insertions. So how can we solve this problem? The answer is using the same procedure, except that we replace dictionary by an Oblivious MAP. We use Oblivious MAP, which proposed by Wang et al. It is based on AVL tree and hides any sequence of operation performed. It uses pass-ORAN for storing AVL tree nodes. Each node contains some information such as ID, ORAN position, children IDs, and children ORAN positions. Now, let me explain it by an example. Suppose we want to look up node 7. We assume that the root of this AVL tree is stored on the client. So at the first step, the client asks for the corresponding path for node 6 and retrieve it, extract it, decrypt and extract the node 6 and compare the target node, which is node 7, by its children. So it knows that it has to go to node 9. In next step, he asks for the path corresponding to node 9 and continues this operation until he gets the final result, which is for node 7. As we can see, to access a node in AVL tree of n nodes, we need log of n interaction by the server. There is only one problem with the oblivious search I described with the OMAP in the previous slide. For each entry, we need log of n interaction. So for NW entries, we need NW log n interaction, which is a lot. So the question is, can we improve this value? The answer is yes. We observe that with OMAP of Wang et al., we can retrieve nodes in batch. Let me explain it by the previous example. Suppose we want to retrieve node 2 and 7 from that tree. First, we fetch the root node, which is 6. At the next step, and for next layer, we fetch all ancestors needed for the future searches. So we fetch both of 4 and 9. So it will be one round. We continue this operation until we get all target values, which is 2 and 7. As we can see, the number of round trips is AVL3 height, which is log n. And finally, for privacy reasons, we always ask for this many nodes per level. Okay, let me explain our experimental evaluation. We implemented our schemes MITRA, ORION, and Horus in addition to 2 schemes from Bost et al. Paper, Fides and Diana Del in C++. We measure search time, update time, and communication size on a synthetic data set of 1,000 to 10 million records. We executed our experiments on AWS machines in single machine, which client and server are on single machine, and over WAN to measure impact of communication. Our code is publicly available. The first experiment is search computation time and search communication size of MITRA, Dianadel, and Fides on a single machine. The x-axis is the result size, which vary from 10 to 100,000. And this experiment is done after 10% deletion, 10% deletion of records. You see that all of these schemes grow linearly by the increase of result size. But MITRA is 253 times, up to 253 times faster than Fides, which is BP2. Even it is faster than Dianadel, which is BP3. MITRA is up to 232 times faster than Fides in update time. And finally, MITRA communication size is 50% worse than Fides. Because of that, the final result, we executed the experiment on a WAN to measure the impact of this communication size on the computation time. So we executed the experiment on a WAN with 21 millisecond latency. As you can see, the breakdown of computation time and communication time and total time. For the small result size, the communication time is dominant, while for big result size, the computation time is dominant. As we can see, MITRA is 1.3 to 51 times faster than Fides, depending on the result size. I have to mention that all our schemes are fully parallelizable, while Fides is inherently sequential. So MITRA can arbitrarily become faster if you have enough sources. But for fairness of evaluation, we executed all of our experiments on a single core machine. Our last experiment is showing the effect of deletions on computation time. ORION and Horus search computation time should be unaffected by the number of deletions and should not relate to the total number of updates. So we executed an experiment over a database size 100,000 and did variable percentage of deletion for a fixed result size. We did this experiment for all of our schemes in addition to Fides and Dianadel. As you can see, the Fides computation time is increasing, while ORION and Horus computation time is constant. MITRA and Dianadel grow too, but they are not visible here. As a final point, this result is encouraging to have schemes with such property because it is constant here. To conclude, we propose 3 backward and forward private schemes. MITRA is the fastest forward and backward private scheme. It is very simple. ORION and Horus are the first forward and backward scheme with quasi-optimal search time. And there are lots of future work for this area. For example, it is good to try remove ORAN from these constructions. Our code is publicly available. If you have any question, I'll be happy to answer it.
Hi, I was just curious, you talk about the 3 different types of leakage.
Yes.
And there's been a lot of prior work exploring, what's lost actually, what can be revealed by these different kinds of leakage. What's known for these 3 types? I mean, do they give meaningful security in the real world?
Well, for the forward privacy, in 2 years ago, there was a paper by Zhang in Usenix, which revealed that if you do not have forward privacy, then documents can be revealed. So there is attack for forward privacy. But for backward privacy, there is not any known attack yet. But maybe in the future, some attack be find out. And the important point is, for example, here in MITRA, we do not pay any extra cost for providing backward privacy. So we can prevent such future attack by using, for example, MITRA.
Hi, thanks for your talk. I just have a general question. So just so I understand, forward privacy is designed to prevent previously issued search token from revealing the keyword of an update before you query it again, right?
Suppose you executed a search. And after that, you execute another update. During update, the server should not learn that the keyword which you are updating is related to, for example, previous search.
Mm-hmm. So, is the only way that could happen is if they just do the search again with the prior search token, or?
The definition is for search. So you search, and after that you update. The information should not reveal to server. The point is, at the search time, the server knows lots of information.
Mm-hmm.
So the information revealed at the update time should not be able to be related to the search time information.
Mm-hmm. But if you could, for example, guarantee that the server is just going to clean up all that information, like using secure deletion or something, do you think that forward privacy would be as important a property? I'm just wondering, like, what's inherent in this forward privacy notion versus what's something that is an artifact of the fact that our systems aren't doing the right thing.
I think you can wipe out the space completely. There's no problem, right?
You with a system
memory completely after the search, then the update will not connect to anything.
Right. Okay, so if you could
use the memory, the search token to do it.
Right, so if you could guarantee secure deletion, then you wouldn't have to worry about forward privacy at all.
It looks to me like it shouldn't be a problem.
Okay, thanks.
But secure deletion, I don't know how you.
Yeah,
you have to consider the cost of secure deletion.
Say again?
You have to consider the cost of secure deletion.
Mm-hmm. Definitely. Okay.